All right, grab your lab coat because today, you and I are partners. We're stepping into the lab to tackle a question that sounds simple but is actually pretty tricky. Is the stuff all around us really pure? Let's get into it. So, first up on our lab bench, think about that carton of milk in your fridge. The label probably says pure milk, right? But is it? Scientifically speaking, the answer is, well, it's probably not what you think. You know, in everyday conversation, pure just means nothing gross has been added to it. But to a scientist, that milk is definitely not pure. It's actually a super complex mixture of water, fats, proteins, all sorts of things. What we call pure in the lab is something else entirely. Okay, so here's the key idea. For something to be scientifically pure, every single one of its tiniest particles has to be exactly the same. We're talking 100% identical. It's made of only one thing. Think of pure sugar, where it's all sugar molecules, or pure salt, where every bit is just sodium chloride. And once you start looking at the world with this new definition, you suddenly realize that almost everything is a mixture. The air we're breathing right now, that's a mix of nitrogen, oxygen, and a bunch of other gases. The soil outside, a mix of minerals and organic stuff, even solid metal things like brass are just mixtures of copper and zinc. All right, for our first experiment, we've got to get organized. We're going to start by sorting all our samples into two big families. And it all boils down to one question. How well are they mixed? So, on one side of the lab bench, we have homogeneous mixtures. Think about stirring salt into water. After a second, you can't see the individual salt crystals anymore, right? It all looks exactly the same, top to bottom. That's a uniform composition. But on the other side, we've got heterogeneous mixtures. Think oil and water. You can shake that bottle all day long and you're still going to see the separate blobs and layers. You can physically see the different parts. Okay, lab partner, time for experiment number 2. Let's get a little more advanced. Some mixtures are sneaky. They look like they're perfectly mixed, but they've got secrets. For this next test, we're going to need a flashlight. So we're going to investigate 3 very specific types of mixtures now: true solutions, suspensions, and this really interesting group in the middle called colloids. And as we'll see, each one behaves a little differently. Now, this table really lays it all out for us. A true solution, like our salt water, has particles so tiny they never settle, and a beam of light passes right through. A suspension, like muddy water, has big particles you can actually see. They'll sink to the bottom eventually, and yeah, they scatter light. But then there's the colloid. The colloid is the tricky one. It looks uniform, and its particles don't settle, but they're just big enough to do something pretty amazing with light. And this is our key test. This special light scattering trick that colloids do, it has a name: the Tyndall effect. It's the secret signal that lets us know, hey, we're not dealing with a simple solution here. And would you look at that? This shows the effect perfectly. On the left, see how the flashlight beam is totally invisible in the true solution? But in the beaker with milk, which is a colloid, bam, you can see the beam plain as day. And this isn't just some weird lab trick. Look at the picture on the right. That's the exact same thing happening when sunlight shines through fog in a forest. The tiny water droplets in the air act like a giant colloid and make the sunbeams visible. So cool. So we figured out how to identify and classify our mixtures. Now for the really fun part. Let's take them apart. Let's see how we can actually separate the individual ingredients from our samples. We're going to start with an easy one from our heterogeneous pile. A mix of 2 immiscible liquids, which is just a fancy science way of saying they don't mix, like our classic oil and water example. For this job, we need a special tool. This thing right here is called a separating funnel, and it is perfectly designed for this one task, all thanks to that little valve at the bottom called a stopcock. It's like a very, very precise tap. The process itself is actually pretty simple. First, we pour our mixture in and we just wait. Since oil is less dense than water, it floats right on top, and you get this super clean line between them. Then we just carefully open the stopcock, drain out the water at the bottom, and shut it off right when the oil layer gets to the bottom. Done. Okay, but what about a tougher challenge? Remember our friend milk, the colloid? The little fat particles that make up the cream are so tiny they'd sail right through any normal filter. So we need a totally different strategy here. And the technique we need is called centrifugation. The idea here is simple but powerful. You just spin the mixture. And I mean really, really fast. This incredible speed creates a force that separates everything out based on its density. And I guarantee you've seen this in action even if you didn't know the name. Dairies use huge centrifuges to separate cream from making butter. The spin cycle on your washing machine, that's a centrifuge, using speed to force water out of your clothes. And it's absolutely essential in medical labs for separating blood cells from plasma for tests. Excellent work today, partner. For our final step, let's analyze our results. We're going to move from just identifying mixtures to actually describing them with numbers. It's time to crack their recipe. So let's say we have 2 beakers of salt water. How can we say, in a really precise scientific way, that one is saltier than the other? We need a way to talk about the strength or the recipe of a solution. The word we're looking for is concentration, and it's basically just that. It's the recipe. It's a precise measure of how much stuff, the solute, is dissolved in the total amount of our solution. And here is one of the most common ways we calculate it. It's called the mass by mass percentage. All we do is take the mass of the solute, divide it by the total mass of the whole solution, and then just multiply by 100 to turn it into a percentage. Let's run the numbers on an example from our lab notebook. Say we dissolved 40 grams of salt in 320 grams of water. Okay, step 1, what's the total mass of the solution? Well, that's the salt plus the water, which gives us 360 grams. Step 2, we plug it into our formula. 40 divided by 360, and then multiply by 100. And there we have it. The concentration of our solution is 11.1%. And that's a wrap on our experiments. We've gone from questioning a milk carton all the way to classifying, separating, and even calculating the recipe for mixtures. So I'll leave you with a final thought. Start looking at your world with these new scientific eyes. What else do you see every day that you thought was pure, but is actually a fascinating mixture just waiting to be explored?